The topic for this video is the following: quantum optimization, mathematical modeling, algorithms, Python programming, and applications. What is the future of operations research? Quantum optimization will play a crucial role in the future transformation process of the world and mankind. Operations research, OR, has long been a cornerstone of decision-making processes, optimizing complex systems and solving intricate problems. As we venture into the future, the landscape of operations research is poised for a substantial transformation with the emergence of quantum optimization. This video explores the profound impact of quantum optimization on the future of operations research, delving into its mathematical foundations, algorithmic advancements, Python programming integration, and applications. Limitations of classical optimization models and quantum optimization. The drawbacks of classical optimization models lie in their limitations in solving complex real-world problems. Classical algorithms often face challenges in handling large-scale combinatorial optimization and dynamic systems. Quantum optimization modeling promises to overcome classical limitations. Leveraging principles from quantum mechanics, they explore multiple solutions simultaneously, enabling more efficient searches through solution spaces. Mathematical foundations and methods of quantum optimization. The mathematical foundations and methods of quantum optimization represent a fascinating intersection of quantum mechanics and mathematical optimization theory. At the heart of quantum optimization lies the mathematical framework of quantum mechanics, a branch of physics that describes the behavior of matter and energy at the smallest scales. Linear algebra plays a crucial role in expressing and manipulating quantum states and operations. The mathematical concepts employed in quantum optimization algorithms include the use of qubits, quantum gates, entanglement, and quantum annealing. Harnessing quantum states and entanglement is a key strategy in designing quantum optimization algorithms. Different quantum optimization algorithms. There are several algorithms for solving quantum optimization problems which are discussed below. Quantum optimization algorithms aim to harness the principles of quantum mechanics to solve optimization problems more efficiently than classical counterparts constrained by the NP-hard problems in these models using different algorithms. One of the prominent quantum optimization algorithms is the quantum approximate optimization algorithm, QAOA. QAOA employs a variational approach, combining classical and quantum components to find near-optimal solutions to combinatorial optimization problems. Another noteworthy algorithm is the quantum annealing (QA) approach. Quantum annealers, such as those developed by D-Wave systems, utilize quantum tunneling to search for optimal solutions in a problem solution space. Grover's algorithm, originally designed for searching an unsorted database, also exhibits optimization capabilities. Grover's algorithm can be adapted to serve optimization tasks by encoding problem constraints into a search space. Recently, variational quantum eigensolver, VQE, optimizes a quantum circuit's parameters to find a given Hamiltonian's ground state energy. As algorithms like QAOA, quantum annealing, Grover's algorithm, and VQE mature, they hold the potential to transform industries by solving complex optimization problems more efficiently than their classical counterparts. Comparative analysis of different quantum optimization algorithms. Each approach has strengths and limitations. AQC and quantum annealing excel in finding global minima, while VQE is versatile but computationally intensive. Grover's algorithm, though powerful, is specific to certain problems. Using Python programming in quantum optimization. Python, a versatile and widely used programming language, plays a pivotal role in harnessing the potential of quantum optimization due to its flexibility, extensive libraries, and vibrant community. One of the most notable libraries is Qiskit, an open-source framework developed by IBM for quantum computing. Qiskit allows researchers and developers to create, simulate, and execute quantum circuits on real quantum processors or high-performance simulators. Hybrid quantum classical optimization approach. Python's versatility extends to hybrid quantum classical optimization techniques. Python allows the seamless integration of classical optimization algorithms with quantum subroutines, creating hybrid solutions that leverage the strengths of both classical and quantum computing. Computational and modeling benefits of quantum optimization. Quantum algorithms significantly reduce computation time for complex optimization problems. Quantum optimization offers unparalleled accuracy, crucial for real-life applications. Benefits in real-life applications of quantum computing and quantum optimization. Quantum optimization's impact extends to real-world scenarios. From logistics and finance to healthcare, we explore how quantum approaches enhance decision-making processes, leading to more optimal and resource-efficient outcomes. Applications of quantum optimization in the real-world environments. As quantum optimization has emerged as a groundbreaking field with diverse applications across various domains, this video reviews the multifaceted landscape of quantum optimization, highlighting its significance in fields such as artificial intelligence, logistics, finance, and cryptography. In the realm of artificial intelligence, quantum optimization algorithms offer a promising avenue to enhance machine learning models. Quantum computers, with their inherent parallelism and ability to process complex data sets more efficiently than classical counterparts, can transform optimization problems central to machine learning. Quantum algorithms can efficiently address combinatorial optimization challenges, aiding in the optimal allocation of resources, minimizing transportation costs, and streamlining supply chain operations. In the financial sector, quantum optimization can profoundly change portfolio optimization and risk management. This can lead to more accurate risk assessment, improved investment strategies, and enhanced financial decision-making. Quantum-resistant cryptographic algorithms are being developed using optimization techniques to ensure the security of information in a post-quantum computing era. Beyond these specific applications, the overarching impact of quantum optimization extends to addressing NP-hard problems across diverse disciplines. The future of operations research appears promising with the advent of quantum optimization. As quantum computing technology continues to mature, the synergy between quantum optimization and operations research is poised to redefine how organizations approach decision-making and resource allocation in the coming years. Therefore, quantum optimization will play a crucial role in tremendously shaping the world's and mankind's future development. The operations research community should embrace this new operations research. Thanks for watching.
This video title is Quantum Chaos Theory. Do we live in a chaotic world? Greetings from Australia. Please subscribe to our YouTube channel. Chaos theory has fascinated scientists, philosophers, and mathematicians alike for decades. Quantum chaos theory explores the interplay between quantum mechanics and classical chaos, addressing the fundamental question of whether quantum systems exhibit chaotic behavior similar to classical systems. Defined by its focus on systems that are deterministic yet unpredictable, chaos theory offers profound insights into the behavior of complex systems. Classical chaos theory emerged as a framework for understanding macroscopic phenomena, such as weather patterns and planetary orbits, that exhibit extreme sensitivity to initial conditions. In contrast, quantum mechanics operates in a realm governed by probabilities and wave functions, challenging the deterministic outlook of classical physics. The interplay between these two domains gives rise to quantum chaos theory, which seeks to reconcile the chaotic behavior observed in classical systems with the probabilistic nature of quantum systems. The question of whether we live in a chaotic world is not merely an academic curiosity. It has implications for understanding the universe's fundamental nature. This video discusses the classical foundations of chaos theory, the emergence of quantum chaos theory, and the controversies and issues that arise when these paradigms intersect. Through this exploration, we aim to address the broader philosophical and scientific implications of chaos in our world. This video also synthesizes current understanding and anticipates future advancements in quantum chaos theory, providing a comprehensive resource for researchers and practitioners in the field. Classical chaos theory. Classical chaos theory originated in the early 20th century with the work of Henri Poincaré, who studied the three-body problem in celestial mechanics. His discoveries revealed that even deterministic systems could exhibit unpredictable behavior due to their sensitivity to initial conditions. This sensitivity, often called the butterfly effect, illustrates how minor changes in the starting state of a system can lead to vastly different outcomes. Key principles. 1. Determinism and unpredictability. While classical chaotic systems are governed by deterministic equations, their long-term behavior is highly unpredictable. 1. This duality challenges the notion that knowing the laws of motion guarantees precise predictions. 2. Nonlinear dynamics. Many chaotic systems are nonlinear, meaning their outputs are not directly proportional to their inputs. 2. This nonlinearity creates complex feedback loops that amplify small perturbations. 3. Fractals and strange attractors. Chaotic systems often exhibit fractal structures, which are self-similar across different scales. 3. Strange attractors, a hallmark of chaos, represent the bounded yet irregular trajectories of such systems. Examples: classical chaos manifests in various natural and human-made systems. Weather models, for instance, rely on equations that are inherently chaotic, limiting their predictive power beyond a few days. Similarly, fluid dynamics, stock market fluctuations, and the motion of celestial bodies exhibit chaotic behavior. These examples highlight chaos theory's utility in explaining phenomena that would otherwise seem random or inexplicable. Despite its successes, classical chaos theory leaves unanswered questions about the fundamental nature of unpredictability, especially when transitioning to the quantum scale. This limitation paves the way for the emergence of quantum chaos theory. Quantum chaos theory. Quantum chaos theory examines the behavior of quantum systems that have chaotic counterparts in the classical domain. Unlike classical systems, which follow deterministic paths, quantum systems are governed by the Schrödinger equation, describing wave functions and probabilities. This fundamental difference complicates the application of chaos theory to quantum mechanics. Key concepts. 1. Wave function dynamics. In quantum chaos, the focus shifts from trajectories to the evolution of wave functions. 1. The interplay between quantum coherence and chaotic dynamics creates patterns that are neither fully random nor entirely deterministic. 2. Semi-classical limit. Quantum chaos often explores the semi-classical limit, where quantum systems begin to exhibit classical-like behavior. 2. This transition is crucial for understanding how chaos emerges in systems bridging the quantum and classical realms. 3. Random matrix theory. A foundational tool in quantum chaos, random matrix theory studies the statistical properties of energy levels in quantum systems. 3. Chaotic quantum systems exhibit level spacing distributions distinct from those in regular systems. Examples: quantum chaos has been observed in various experimental setups, such as quantum billiards, where particles are confined within irregularly shaped boundaries. These systems reveal chaotic patterns in the distribution of energy levels and wave functions. Similarly, chaotic dynamics in quantum dots and atomic nuclei provide insights into energy transfer and stability in complex systems. By exploring these phenomena, quantum chaos theory challenges traditional views of randomness and determinism, raising profound questions about the universe's underlying order. Controversies and issues. the intersection of classical and quantum chaos theories sparks significant controversies and challenges, both philosophical and practical. These issues stem from the fundamental differences between the deterministic nature of classical physics and the probabilistic framework of quantum mechanics. Quantum chaos theory seeks to reconcile the deterministic equations of quantum mechanics with the sensitive dependence on initial conditions typical of classical chaos. Critics argue that quantum mechanics, with its wave function evolution, does not allow for chaos in the classical sense, leading to debates on the existence and definition of quantum chaos. Pioneering works by researchers like M. Gutzwiller have set the stage for these discussions, emphasizing the need for a clearer conceptualization of chaos in quantum systems. Philosophical debates. 1. Determinism versus probabilism. Classical chaos operates within a deterministic framework, where unpredictability arises from sensitivity to initial conditions. 1. In contrast, quantum mechanics is inherently probabilistic, governed by the uncertainty principle. 1. Reconciling these paradigms raises questions about the nature of reality. 1. Is chaos a fundamental feature of the universe, or is it a construct of human models and limitations? 2. Nature of chaos. Some argue that chaos in quantum systems is an artifact of approximations used in modeling. 2. Others contend that quantum chaos reflects a deeper, intrinsic property of the quantum world. 2. This debate influences how we interpret the transition from quantum to classical regimes. Measurement challenges. Quantum systems are notoriously difficult to measure without disturbing them, complicating the study of chaotic behavior. The act of observation collapses quantum wave functions, potentially masking chaotic dynamics. This observer effect underscores the limitations of experimental investigations into quantum chaos. Heisenberg uncertainty and chaos. The Heisenberg uncertainty principle, which limits the precision of simultaneous measurements of position and momentum, introduces an additional layer of complexity. In classical chaos, precise initial conditions are crucial for predicting system behavior. In quantum systems, this precision is fundamentally unattainable, raising questions about whether quantum chaos can truly mirror its classical counterpart. Interdisciplinary implications. Quantum chaos theory intersects with various fields, including quantum computing, material science, and cosmology. However, its interdisciplinary nature also introduces challenges, as researchers must navigate differing terminologies, methodologies, and goals. These challenges highlight the need for collaborative approaches to advance the field. Mathematical foundations. The study of chaos, both classical and quantum, relies heavily on mathematical tools to describe and analyze complex systems. In quantum chaos, these tools bridge the gap between probabilistic quantum mechanics and the deterministic framework of classical physics. This section reviews the mathematical tools and techniques used to analyze quantum chaotic systems. It includes discussions on quantum ergodicity, the random matrix theory, and semi-classical approximations. These mathematical models help describe how classical chaos manifests in quantum systems, particularly in the study of quantum billiards and spectral statistics. Reference works such as Chaos in Classical and Quantum Mechanics, by M. Gutzwiller provide a deep dive into these topics. Key mathematical tools. 1. Lyapunov exponents. These quantify the rate at which trajectories in phase space diverge, a hallmark of chaos. 1. While well defined in classical systems, adapting Lyapunov exponents for quantum systems remains an ongoing challenge. 2. Random matrix theory. This mathematical framework models the statistical behavior of energy levels in chaotic quantum systems. 2. The level spacing distribution provides a signature of chaos and distinguishes between regular and chaotic quantum systems. 3. Semi-classical analysis. Techniques such as the WKB approximation bridge the gap between quantum and classical systems, offering insights into how chaotic behavior emerges as systems scale. 4. Fractal geometry. Fractal structures in phase space, such as those found in strange attractors, offer a visual and analytical representation of chaos. Applications in mathematical modeling. These mathematical tools allow scientists to create predictive models for quantum systems exhibiting chaotic behavior. They also help identify patterns and structures within seemingly random phenomena, deepening our understanding of underlying processes. Technologies, simulation and programming technologies. Technological advancements have enabled precise experiments that test theoretical predictions related to quantum chaos. This includes the development of quantum computers and specialized quantum simulators that model chaotic systems. Technologies like laser cooling and trapping have also been instrumental in studying quantum chaos in atomic and molecular systems. These tools help validate the theoretical frameworks and bring practical insights into the behavior of quantum systems under chaotic conditions. Role of simulation. Simulations are indispensable for studying quantum chaos, as analytical solutions are often impossible due to the complexity of these systems. Simulations provide a way to test theoretical predictions and explore chaotic behavior in controlled settings. Algorithms and programming tools. Programming in quantum chaos involves the implementation of complex quantum algorithms on classical and quantum computers. This section reviews the programming languages and environments such as Qiskit and Cirq, which are used to simulate quantum chaotic systems. The development of efficient computational methods and the use of high-performance computing resources are essential for the large-scale simulation of quantum chaos. Several algorithmic approaches have been developed to simulate and analyze quantum chaotic systems. This includes algorithms for quantum walks, which are crucial for exploring the dynamics of quantum particles in a chaotic environment. Algorithms based on the Fourier transform and wavelet analysis also play a significant role in identifying chaotic patterns in quantum systems. These methods are critical for advancing our understanding of how quantum information behaves in chaotic systems. 1. Python. Widely used in scientific computing, Python libraries such as NumPy, SciPy, and Matplotlib are instrumental in modeling and visualizing chaotic systems. 2. Quantum-specific libraries. Tools like Qiskit and Cirq allow researchers to simulate quantum systems, incorporating chaos into quantum circuits and algorithms. 3. MATLAB. This software is particularly useful for handling large-scale numerical computations required in quantum chaos studies. Challenges in simulation. 1. Computational complexity. Simulating chaotic quantum systems requires significant computational resources due to their high-dimensional state spaces. 2. Noise and decoherence. Quantum systems are highly sensitive to environmental disturbances, complicating the simulation of idealized chaotic dynamics. Examples of simulated systems: quantum billiards, spin chains, and quantum dots are among the systems commonly simulated to study chaos. These models provide insights into real-world phenomena, such as energy transfer and stability in materials. Real-life applications in different areas. The applications of quantum chaos are vast and include quantum cryptography, quantum computing, and the development of highly sensitive quantum sensors. Quantum chaos principles are used to enhance the security of quantum key distribution systems and to develop algorithms that improve the efficiency of quantum computations. Additionally, understanding quantum chaos can lead to better control strategies in quantum technologies, impacting fields like material science and telecommunications. Some of the significant applications of quantum chaos theory are discussed below. Quantum computing. Chaos plays a critical role in understanding error propagation and developing robust quantum error correction codes. Studying chaotic dynamics in quantum circuits helps improve the reliability of quantum computers. Material science. In disordered systems, quantum chaos influences energy transfer, conductivity, and stability. These insights are vital for developing advanced materials, such as superconductors. Astrophysics. Chaotic quantum systems provide models for phenomena such as black hole dynamics and the distribution of matter in the universe. Biology. Quantum chaos has potential applications in understanding molecular dynamics and enzymatic reactions, offering insights into complex biological processes. Do we live in a chaotic world? The question of whether we live in a chaotic world hinges on our perspective. At the macroscopic level, classical chaos theory demonstrates that deterministic systems can produce unpredictable outcomes. At the microscopic level, quantum chaos suggests that even probabilistic systems exhibit patterns of unpredictability. Integration of perspective. By integrating classical and quantum chaos theories, we gain a more comprehensive understanding of the interplay between order and randomness. This dual perspective highlights the layered complexity of our universe. Philosophical implications. The coexistence of order and chaos invites philosophical reflection on the nature of reality. Is chaos a fundamental property of the universe, or is it a consequence of human limitations in modeling and observation? Scientific and practical implications. From improving quantum technologies to advancing our understanding of natural systems, studying chaos has profound implications for both science and society. Whether we live in a chaotic world may remain an open question, but the exploration of chaos continues to drive innovation and discovery. Limitations and future directions. While significant progress has been made, the field of quantum chaos still faces several limitations and requires improvements. These include the difficulty in experimentally verifying theoretical models and the challenge of scaling quantum simulations for complex systems. Future research directions for improvement may focus on developing more robust theoretical models that bridge the gap between quantum and classical chaos, enhancing computational methods for better simulations, and exploring new applications in quantum technology. Conclusion. The study of quantum chaos bridges the deterministic and probabilistic realms, offering a deeper understanding of the universe's inherent complexity. While the world may appear chaotic, it is within this chaos that the patterns and structures of reality emerge. Thanks for watching. Don't forget to subscribe to the channel for your success. If you like this video, please give it a thumbs up.
Greetings from Australia. Please subscribe to our YouTube channel. Quantum game theory, an emerging field at the intersection of quantum mechanics and game theory, holds the potential to transform problem solving in some of the world's most challenging and complex scenarios. By harnessing the power of quantum computing and applying game-theoretic principles, researchers aim to tackle pressing issues like optimization, decision-making, and strategic planning with unprecedented efficiency and accuracy. This video discusses quantum game theory and its following topics. 1. Theory, framework, principles and concepts. 2. Mathematical structure, modeling and models. 3. Solution algorithms. 4. Python programming. 5. Results. 6. Implications. 7. Applications. 1. Theory, framework, principles, and concepts. Quantum game theory combines concepts from game theory, quantum mechanics, and information theory such as the following. A. Superposition. Quantum game theory allows players to be in superposition states, where they can exist in multiple strategies simultaneously. B. Entanglement. Players can become entangled with each other, meaning their states are correlated and cannot be described independently. C. Quantum strategies. Players can employ quantum strategies, represented by quantum states and unitary operators. These strategies can be used to manipulate the game's outcome. D. Quantum payoffs. Quantum game theory also introduces the concept of quantum payoffs, which can be entangled with the strategies and outcomes of the game. E. Quantum measurements. Quantum measurements are used to extract classical information from quantum systems. In quantum game theory, these measurements can be used to determine the player's final outcomes. 2. Mathematical structure, modeling, and models. The mathematical structure of quantum game theory builds upon the framework of classical game theory. It employs elements from linear algebra, quantum mechanics, and game theory. The basic model used in quantum game theory is the quantum version of the normal form game, which consists of A. Players. The game involves multiple players who make strategic decisions. B. Strategies. Each player has a set of strategies available to them, including classical and quantum strategies. C. Quantum states. Players' strategies are represented by quantum states in a Hilbert space. D. Unitary operators. The player's actions are described by unitary operators that transform their quantum states. E. Payoff operators. Hermitian operators represent quantum payoffs that act on the player's quantum states. 3. Solution algorithms. Using quantum principles, finding solutions to quantum games involves analyzing the strategic choices and outcomes. Several solution algorithms have been developed for different types of quantum games, including the following. A. Quantum Nash equilibrium. The concept of Nash equilibrium is extended to quantum games, where players' strategies are in equilibrium if no player can unilaterally change their strategy to obtain a better payoff. Finding quantum Nash equilibria can be complex, and various numerical and analytical techniques have been proposed. B. Quantum game solvers. Several algorithms, such as the quantum Monte Carlo method and the variational quantum eigensolver, have been adapted to solve specific types of quantum games. 4. Python programming. Python programming is widely used in quantum game theory for simulation, analysis, and implementation of quantum algorithms. Python libraries such as Qiskit, PyQuil, and Cirq provide tools for working with quantum states, operators, and algorithms. 5. Results from quantum game theory models. Quantum game theory has produced several notable results, demonstrating quantum strategies' unique aspects and potential applications. Some key findings include: A. Quantum advantage. Quantum strategies have been shown to provide advantages over classical strategies in specific game scenarios, leading to higher payoffs or increased cooperation between players. B. Quantum prisoner's dilemma. The prisoner's dilemma, a classic game used to study cooperation and conflict, has been analyzed using quantum game theory. It has been shown that entangled quantum strategies can lead to increased cooperation between players. C. Entanglement and coordination. Quantum game theory has revealed the role of entanglement in coordinating actions between players and achieving optimal outcomes in certain games. 6. Implications. The implications of quantum game theory extend beyond theoretical research and have potential practical implications. A. Quantum computing. Quantum game theory provides insights into the utilization of quantum computing for solving complex strategic problems. It showcases how quantum algorithms and strategies can enhance decision-making in various domains. B. Quantum cryptography. Quantum game theory offers a framework for understanding the security and protocols of quantum cryptography, and the interplays between quantum strategies and cryptographic scenarios. C. Quantum communication and networks. Quantum game theory can aid in designing and optimizing quantum communication protocols and networks for studying cooperative behavior and resource allocation in quantum information exchange. D. Quantum economics. Quantum game theory has been applied to economic scenarios, such as auctions and bargaining. It explores the impact of quantum strategies on market dynamics, pricing mechanisms, and efficient allocation of resources. E. Quantum social sciences. Quantum game theory can contribute to social sciences by offering new insights into decision-making, cooperation, and conflict resolution. 7. Areas of applications. Quantum game theory finds applications in various fields, including: A. Quantum cryptography. Quantum game theory is relevant to the analysis and development of secure communication protocols based on quantum principles. B. Quantum computing. It helps in understanding the potential applications of quantum computing, including optimization, machine learning, and simulations. C. Quantum economics and finance. Quantum game theory can aid in modeling financial markets, risk assessment, portfolio optimization, and strategic decision-making in quantum financial systems. D. Quantum communication networks. It contributes to the design and analysis of quantum communication networks, including secure quantum key distribution and quantum teleportation protocols. E. Social sciences. Quantum game theory can be applied to sociology, psychology, political science, and other social sciences to study decision-making, cooperation, and group dynamics. Thanks for watching.
Title: Multi-Agent Game Theoretic Quantum AI Agents and the Transformation and Efficient Management of the World, Technologies, Algorithms, Programming, and Profound Applications. Introduction. The world is increasingly managed by intelligent systems embedded within complex networks of autonomous processes, distributed control, economic exchange, and digital infrastructure. In this landscape, decision-making is no longer centralized, linear, or predictable. It is strategic, interactive, probabilistic, and multi-agent in nature. To design, understand, and manage such systems efficiently, we now draw from three of the most significant intellectual and computational paradigms developed by humankind: game theory, artificial intelligence, and quantum computing. Each of these paradigms independently contributes to the science of systems reasoning, adaptation, and optimization. But their integration, specifically within the construct of multi-agent game theoretic quantum AI agents, ushers in a new foundation for scalable, intelligent, strategic, and computationally enhanced decision architectures. These agents can simulate, learn, anticipate, and compute optimal responses under interdependence, uncertainty, and constraints in ways that classical systems cannot. The practical value of this unified paradigm spans global policy design, economic management, infrastructure coordination, security systems, and intelligent governance mechanisms. These are not abstract visions, but real systems already in design, simulation, and pilot deployment. Call to collaboration. In light of the strategic significance and complexity of multi-agent game-theoretic quantum AI agents, we extend an early and open invitation to industry leaders, researchers, institutions, policymakers, and developers across disciplines. This is a call to co-develop mechanisms, protocols, and platforms that reflect a deep synthesis of strategic intelligence, computational efficiency, and quantum-enhanced simulation. Join us in shaping the direction of this integrated technological frontier. The strategic significance of game theory. Game theory remains the fundamental logic that enables reasoning under interdependence. It offers a mathematically rigorous framework for strategic behavior, equilibrium design, incentive alignment, and rational choice in systems with multiple agents. At its core, game theory models how the outcome for any one agent depends not only on its own decisions but also on the decisions of others. It formalizes equilibrium concepts such as Nash, correlated, Stackelberg, and Bayesian equilibria, and provides mechanisms for stable cooperation, negotiation, conflict resolution, and efficiency optimization. Its significance in shaping human understanding of competitive and cooperative systems has been recognized repeatedly by Nobel Prizes, awarded to John Nash for equilibrium theory, Thomas Schelling for modeling strategic conflict and deterrence, Alvin Roth and Lloyd Shapley for algorithmic market design, and Paul Milgram and Robert Wilson for auction frameworks that guide modern digital economies. These achievements have directly informed the architecture of AI agents operating in competitive online platforms, defense simulations, smart markets, and decentralized governance mechanisms. As we integrate game theory with quantum and AI capabilities, its role becomes even more vital for defining stability, fairness, and efficiency in systems that are computationally enhanced, interactive, and probabilistically modeled. The computational power of artificial intelligence and quantum computing. Artificial intelligence enables adaptive systems to perceive environments, infer latent patterns, optimize actions, and update strategies based on experience. Through reinforcement learning, deep learning, model-based inference, and multi-agent control, AI has become a core building block in intelligent infrastructure. However, in complex settings where interactions between agents are strategic and continuous, AI alone is insufficient. Game-theoretic reasoning fills this gap by enabling agents to model, anticipate, and counteract the actions of others. Meanwhile, quantum computing introduces a fundamentally different computational substrate. It offers the ability to represent, explore, and manipulate information in high-dimensional and entangled state spaces that grow exponentially with problem size. This includes the application of quantum-enhanced optimization algorithms, variational circuits for quantum policy learning, and quantum sampling methods for equilibrium exploration in stochastic environments. When quantum algorithms are integrated with AI models that have embedded game-theoretic reasoning, we arrive at a paradigm capable of computing equilibria and policies under constraints that would otherwise be infeasible. These agents are not only adaptive and strategic, but also computationally empowered to handle interdependencies that exceed classical limits. Programming such agents involves hybrid architectures, including Qiskit, TensorFlow Quantum, PennyLane, and quantum multi-agent simulation frameworks using OpenSpiel and custom quantum learning circuits. Integration into multi-agent game-theoretic quantum AI agents. The multi-agent game-theoretic quantum AI agent represents the integration of three foundational components. First, its learning core is based on deep reinforcement learning, enabling continuous adaptation through interaction. Second, its reasoning layer is governed by game-theoretic algorithms such as fictitious play, regret matching, quantal response equilibria, and policy learning in extensive-form stochastic games. Third, its computational backend leverages quantum processing for solving combinatorially complex optimization problems, representing probabilistic policies through quantum circuits, and exploring payoff distributions in entangled decision environments. These agents are capable of learning and deploying policies in high-dimensional, multi-agent strategic spaces with incomplete and evolving information. They are able to compute approximate and exact equilibria in dynamic games, perform opponent modeling using quantum-enhanced Bayesian inference, and coordinate under decentralized, partially observable settings. Architecturally, these agents can be deployed across cloud-edge quantum environments for real-time learning, control, and decision support. Programming them involves combining TensorFlow Quantum or Qiskit runtime environments with game-theoretic solvers and learning algorithms implemented in Ray RL-lib, petting zoo, or custom frameworks. Through this integration, agents exhibit strategic robustness, computational precision, and adaptive behavior beyond the limits of traditional intelligent systems. Applications for global transformation and efficient management. Multi-agent game theoretic quantum AI agents have wide-ranging applications in the efficient management and transformation of systems at scale. In strategic security and defense, they support cyber threat prediction, autonomous mission coordination, and secure information sharing through quantum-safe communication. In energy systems, they manage decentralized optimization of generation, distribution, and demand pricing under market constraints and strategic agent participation. In healthcare, they enable coordinated triage, epidemic modeling, and strategic allocation of scarce medical resources during crises. In smart cities, they govern autonomous vehicle routing, real-time traffic control, and decentralized infrastructure operation through congestion-aware strategy learning. In finance, these agents execute quantum-enhanced algorithmic trading, arbitrage, and mechanism design for transparent and incentive-aligned marketplaces. In global diplomacy, they simulate treaty dynamics, model coalition formation under climate and economic constraints, and support coordinated international action through strategic alignment models. In supply chains, they optimize vendor contracts, logistics networks, and coordination games in dynamic, uncertain environments. These applications demonstrate the viability of multi-agent strategic intelligence as a framework for practical implementation in large-scale socio-technical systems. Conclusion and strategic direction forward. The integration of game theory, artificial intelligence, and quantum technologies represents a foundational transformation in how the world can be understood, managed, and improved. Multi-agent game theoretic quantum AI agents bring together strategic reasoning, adaptive learning, and quantum computational power into one coherent system capable of addressing challenges in infrastructure coordination, global negotiation, autonomous planning, and intelligent policy design. These systems are critical for enabling scalable, equitable, and resilient responses to increasingly interdependent global problems. We invite all relevant stakeholders to collaborate in this domain. Researchers can contribute algorithms, models, and simulations. Engineers can implement platforms, interfaces, and real-time integration tools. Policymakers can design regulatory frameworks that guide ethical deployment and fairness in strategic environments. Educators can train the next generation of engineers, scientists, and designers to work at the intersection of AI, game theory, and quantum computing. Subscribe to this platform for ongoing series, technical demonstrations, applied case studies, and collaborative research updates. This is not merely the next wave of computing, it is the architecture of strategic intelligence for the future. Let us build it together. Please contact Professor Dr. Sardar M. Islam, NAS, to collaborate on industry applications, publications, workshops, open source tools, and joint ventures. Email address is sardar.islam@vu.edu.au. Join us in building the strategic operating systems that will transform and manage the world wisely and efficiently. Let's design the future of intelligent decision-making, together.